In the next few slides, we're going to be talking a little bit about spontaneous redox reactions. How can we identify if a redox reaction is spontaneous? So will it liberate electrons? Or if it's non-spontaneous, if you want it to happen, you will have to provide those electrons, that voltage for the reaction to happen. The energy released in a spontaneous reaction, like for example, we were talking about endothermic and exothermic reactions, we were talking about heat. Heat release, heat being absorbed, exothermic and endothermic reactions. When you're looking at redox reactions, we're not looking about heat, you're talking about work, electrical work. So a spontaneous redox reaction will liberate electrons. Those electrons, will be liberated. They will have a flow, a natural flow of electrons. The reaction will happen and the electrons will move from one compound to the other. And in that movement from one compound to the other, we can harness that movement by making them go through wires and produce electrical work. And we talk about electrode potential because we think about electrical work as, the fact that the electrons transfer spontaneously from one compound to the other as the same as potential energy. When you have water flowing down a water flow, you have a difference in height and the water falls, and that difference in the potential energy between the top of the waterfall and the bottom, from the water at the top of the waterfall and the bottom in the stream or lake, that potential energy, because of the height difference, allows it to potentially do some work. The same happens with electrons, or the same. In a similar way, you can think about electrons flowing spontaneously from one compound to the other as a sort of a waterfall, falling from one compound into the other, and that transfer is that potential energy can be harnessed and used to perform electrical work. So what do you do to get electricity out of your spontaneous redox reaction? Well, you let the ions and the compounds touch each other, but you don't let the electrons flow spontaneously throughout the solution. You conduct the electrons through wires. And this is an example of, this is a typical example of what we call a galvanic cell. A cell which is based on a spontaneous redox reaction, in which you allow the ions and the compounds to transfer between the oxidation reaction and the reduction reaction, but you don't let the electrons flow. The electrons flow through a wire, and in that process of moving from the oxidation half reaction to the reduction half reaction, they produce electrical work for you. The anode is where the oxidation happens, so where the loss of electrons happens, and the cathode is where the reduction happens, where the electrons are gained. And there is a difference in the potential energy between those two electrons. That electron flow, like in the case of a water flow, remember I was talking about the water falling from this, from the waterfall down into the stream. In this case, the electron is flowing from the section of the reaction, the anode, where the electrons are lost, to the part of the cell of your chemical reaction where the electrons are gained. And there is that difference in potential energy between those two electrodes. We call that electromotive force, EMF, or electrode potential. And you sometimes see the acronym EMF, or you can just use the letter E to talk about this electromotive force or electrode potential. And for a redox reaction to be spontaneous, that E, that electromotive force, must be a positive number. So if that electromotive force, if that electrode potential is positive, that means that the electrons flow naturally from the anode to the cathode. If that number is not a positive number, then the reaction will not happen spontaneously. If you wanted it to happen, you will have to apply that voltage for the reaction to force the electrons to flow. So what do? Well, we measure the tendency of any element you can think of to lose or gain electrons and how many it loses or gains. And we measure the electromotive force, the electropotential that reaction would have. And if it's a positive number, then that reaction does happen spontaneously. And if it's a negative number, it means that reaction will not happen spontaneously. If you wanted it to happen, you will need to apply that amount of voltage. We need to measure it against something, because a redox reaction only happens if you have to halve something that loses electrons and something that gains electrons. So to make a voltaic cell, you need to half cell. You cannot measure the tendency of an element to reduce, that is to gain electrons, if you don't have something that is going to lose electrons for that element to gain them. So what we do is we compare all the possible reactions to compare. We use hydrogen, the reaction of two hydrogen ions that gains 2 electrons to produce hydrogen, the compound H2, dihydrogen. And we set up a voltaic cell involving any element you can think of losing or gaining electrons, compared to, and the other electrode being with a hydrogen reaction. That's what we call the standard hydrogen electrode. And we assign the value 0 to this reaction, 2 hydrogen ions plus 2 electrons to produce the compound H2. And we call that the reference electrode. The standard hydrogen electrode, it has different, or the standard, the hydrogen electrode, the hydrogen reference electrode, it has several names depending on the books. And that's how you work out all the standard potentials of all the other elements, setting up a voltaic cell between that element and the hydrogen electrode as the reference. And you measure the difference in voltage, and then you do know how that reaction happens with respect to hydrogen, and you assign hydrogen, that reaction of hydrogen, the value 0 volts. And if it's a positive number, what you end up with, then that reaction would be spontaneous as you have written it. If it's a negative number, it's not spontaneous in that way. It would be spontaneous in the other way, going in the other direction. So this is an example of how a table of standard reduction potential looks like. Or standard potentials measuring volts. We have the superscript 0. And that is because they are measuring what we call standard conditions. 25 degrees temperature, concentration of the compounds is 1 molar, pressure, atmospheric pressure. So that's what we call, because the behavior of our cell will depend on the temperature, will depend on the pressure, will depend on the concentration of the reagents, and we can talk briefly about it in a future slide. So that's what the super 0 means. It means what we call standard conditions. All the concentration of the reagents and products is 1 molar. The temperature is 25 degrees, 298 Kelvin, and if there are any gases, the gases again have a pressure of 1 atmosphere. And as you see, all the tables are given as a standard reduction potential. So they are all written as reduction reactions. But when we actually construct our cell, we will know that the reaction in the oxidation side of the cell, in the anode, will need that number change, because what we are looking at is the reaction going the other way as an oxidation.